Welcome to Data Skeptic K-means Clustering, the podcast exploring the problem, the algorithms, enhancements, and use cases for K-means clustering. For pedantic listeners, let me point out an error I've made a few times this season. There is no K-means clustering algorithm. K-means clustering is the problem. There are a variety of algorithms that attempt to give you the best solution they can. Lloyd's algorithm is the most famous. Previous episodes have touched on K-means ++, a few times actually, in which a clever initialization of your first set of randomized centroids offers an improvement to the plain vanilla Lloyd's algorithm. We then learned about power K-means and breathing K-means, which offer improvements in the iterative algorithmic process, rather than the initialization. There's a bunch of similar algorithms we didn't have time to feature on the podcast, all of which allow a user to achieve either a better clustering result, faster clustering results, or both, through whatever their particular insight or enhancement is. In this final episode of our official season on K-means clustering, I speak with Jonas Landman about Q-means clustering. Q-means is an enhancement to Lloyd's algorithm that takes advantage of quantum computing during each iteration of the algorithm.
Hi, I am Jonas Landman. I'm French, I'm from Paris, and I have obtained my PhD from the University of Paris in France as well. And before that, I was studying at UC Berkeley and École Polytechnique. And right now, I am a postdoc at the University of Edinburgh in Scotland. And on the same time, I'm working at the company QCware in Paris.
Very cool. What was the focus of your PhD?
Well, the main focus was the quantum algorithm for machine learning. So quantum algorithm meaning algorithm that you could implement on a quantum computer. And in particular, I was studying unsupervised machine learning and neural networks.
And are you studying similar topics in your current postdoc?
Yes, exactly. So it's still about quantum computing and what we can do with them. The difference in my postdoc is that I am focusing on near-term application, whereas in the PhD I was looking at, the general idea of a quantum computer in the long term, maybe a perfect one, let's say a fault-tolerant and universal quantum computer, as we say.
It's very interesting because, a lot of my understanding of quantum computers in general is that there's no reason they won't work. The physicists have no complaints. Everyone agrees that they're there. We just don't really have a practical industrial scale one yet. What are some of those near-term problems that might be solved sooner than, the ultimate experience of the greatest quantum computer?
It's a very important distinction to make, I guess. I often talk about near-term and long-term. Of course, it's more of a continuum between the two. But let's say that it's mainly an engineering issue. That being said, I'm not a physicist and not an experimentalist, so I will not explain how and why it doesn't work that well right now. Yeah, I think it's a matter of understanding how to put nature in a box while she doesn't want to, somehow. And about the near-term application, I don't know, it's more about the near-term spirit or approach, I would say. This is well characterized in the sense that on the long term, you don't really care about the size of your quantum computer or the fact that the quantum gates and the qubit, we might define that later, but the quantum gates and the qubit are noisy, so that in the long term you don't care. In the short term, you really do care, and you take into account the fact that you want a quantum circuit that is very small and shallow, as we say. But we will define this term later if you want.
Yeah, maybe we could start with kind of a high-level question. I feel like today we can expect the listeners will be aware of quantum computers, but maybe a common misconception is that it's just sort of this boost all around, that if you upgrade to quantum, your computer just gets universally better. But actually my understanding is that it's in specific cases. Or could you share some detailed insight about what is it about quantum computing that's better than classical computing?
Yes. I understand that it could feel a bit mysterious because everything that has the word quantum inside is a bit mysterious. For sure, it's not a faster classical computer. It's the fact that we are changing really the paradigm of computing. So if you're familiar, you would know that classical computing, we tend to forget about it. But in our phone, in our computers, there are millions or billions of transistors. These are little tiny switches, let's say, electrical switches that can be in two states. And these states, we call them 0 and 1, for instance. Quantum computing is the idea of not using these switches as like with these transistors, but to use, for instance, states of an ion, states of a light, cold atom, or whatever, is small enough to have a quantum nature. And this quantum nature, if you have two states, for instance, an ion which is excited on the ground state, well, there is one fundamental property of quantum physics is that they can be in superposition of these two states. Superposition means that you are in both states at the same time, which really doesn't make sense for us, but it's true. And the idea is that you can be in some, let's say, in some probability in one state and probability in the other state. But actually, it's not a probability in the sense that you really are in both states. So it's a very big shift in terms of you're not 0 or 1, you're not open or closed, but you can be in both states. Starting from that, it's a super different way of approaching computing.
I see quantum algorithms in many contexts, but I'm glad you worked specifically on quantum machine learning, because I think my listeners will be especially attuned to how machine learning algorithms work, or at least understanding some of the common structures of logistic regression and decision trees and neural networks and things like that. And we've been doing this series on k-means, so hopefully if they've heard the recent episodes, they're familiar with this algorithmic technique. Couple of steps, right? We assign centroids, we remap them, we update. It's this optimization problem. Where can something quantum come into the mix?
When I first wanted to do any kind of quantum algorithm applied to machine learning, it was the question I asked myself, like, what does it mean to use a quantum computer? So there are different strategies, I would say. The first one would be, okay, let's look at k-means. Let's look at one step in particular that might take time. And let's try to see if this specific step we cannot delegate it. We cannot give it to a quantum computer to solve. And usually you would take the step that is the most computationally intensive. That being said, in k-means, nothing is extremely intensive, right? Because if you have n data points, the algorithm is linear in n, in the sense that it's not an exponential algorithm or something like that. So that's the first strategy, right? Take one step and try to do it quantumly. The other strategy would be, no, let's not take one step. Let's take the whole algorithm. I choose centroids. I can compute all distances. Then I update the centroid and so on. So that would be another strategy. Final strategy would be maybe let's do something extremely different, but that does some kind of clustering. But this is a bit more not k-means. But yeah, just to sum up, how quantum could help in any machine learning.
Well, if we step back from k-means and we think about it in just a functional way, it's a function that I give my data set to, and out comes some partitions, right? A mapping from my data points to what clusters they go in. Now, we know k-means goes through some specific steps. Do you just step back and process that all at once, or what's the general quantum version of the algorithm?
Yeah, so in the paper I wrote that was published in NeurIPS 2020, I guess, or 2019, I don't remember, but one of these years, we did a full k-means in a way, like the quantum appears at all steps. And the main contribution, I would say, of this work is to be able to compute the distance between 2 points using a quantum circuit. And the interesting part is that, so I asked myself the question, how do you compute the distance between 2 points? Because it feels so usual, right? If you write code, you just compute the distance. And now I was like, okay, no, to compute the distance, you have to take the two vectors, you have to understand their components, each part of each dimension, and you have to compute an inner product, something like that. And then you start to understand what is going on really, understand how a classical computer is computing an inner product, etc. And quantumly, the good thing is that it can be done exponentially faster, with the assumption that you have the vector as quantum state in the input and the distance as also kind of a quantum state in the output. But the good thing is that we are also able to compute the distance not only between 2 points, but in superposition of many points. So, and this is where you use this power of quantum computing. So, as I said, if you start with one quantum state, or let's say two quantum states that you want to compare, that you want to compute the distance, you can do it fast. But now, because I can be in superposition in quantum, I would start not only with two vectors, but with a superposition of many vectors on one hand and a superposition of many vectors on the other hand. If I would compute the distance between these two inputs, I would end up with a superposition of all the distances, all the pairwise distances. So that's behind our reach. And this is where kind of the magic, this is where it takes place.
It makes sense. One of the cognitive challenges for me in understanding quantum algorithms was appreciating the no-clone theorem, that even though I could put something in a quantum state, I could only read it once. So what do I do with it once it's there? And in the way I explain it, it's like you have a superposition and then you iteratively amplify it so that the likelihood you would select the correct answer it goes up, the likelihood you'd select the incorrect answer goes down. Is that a proper intuition? Does it apply in this case?
Okay, so yeah, the non-cloning theorem says exactly that you can teleport a quantum state, right? You can copy a quantum state, but you have to destroy the original. That's what it says somehow. I mean, by the way, the k-means algorithm, quantumly, we named it the q-means algorithm, of course. But in the case of the q-means, we didn't have this issue of handling the fact that you do not copy a quantum state. There are several reasons, but also we need to keep in mind that in the end, the input is classical and the output is classical. So the input are like these points and these centroids, and the output is like updated centroids somehow. And so because we are thinking about the end-to-end algorithm, you can clone classical data. So each time you want to start over, you will start by again loading your classical data and outputting your classical output. So yeah, just to say that we didn't have this problem for non-cloning.
Well, in the traditional k-means problem, it's an NP-hard problem. I'm not going to solve it efficiently. I'm going to get maybe epsilon close to the correct answer. How does q-means work?
Of course, there is no solution to the exact clustering. So we use this kind of iterative heuristic, which is k-means. And the idea of q-means now is to follow exactly the same step as a k-means. So if you understand k-means, you understand the step, it's going to be the same quantumly. It's just that some part will be done, as I said, in superposition. Some calculation, like the distance estimation, will be done using quantum circuits that are extremely different. But in the end, we want the same thing. We want to start with some centroids and update them and repeat as many times it's needed. So we are not like solving this NP-hard problem faster. We are just giving some kind of speed up to the k-means algorithm.
I'd love to revisit the notion of distance again. Can you remind me, are there any key insights? How does the quantum algorithm make distance calculations such a speed up?
Yeah, so one should maybe go to the mathematical details to understand it. But yeah, let's say that the intuition I can give is that when you deal with quantum circuits, you play with these probabilities I told about in the beginning. These probabilities, actually, we call them the amplitudes. So, for instance, if I have a quantum state which is both in state 0 and 1, well, it will have some amplitudes of being in state 1 and some amplitude of being in state 0. And because these amplitudes are linked to probabilities, they must sum up to 1, right? But to be very precise, these amplitudes are complex numbers, so it's not that simple, but okay. The idea now to compute the distance is to play with the amplitudes so that relevant information becomes, you want to be sure that the relevant information ends in some of the amplitudes. In this case, what we want to do is that the probability of measuring some qubit in the state 1, so it's a qubit that I control somehow, and I can prove that the probability of measuring it in state 1 will be proportional to the inner product between the two vectors, the two input vectors. So once I know that some amplitude is proportional to this input vector, again, I can play with this amplitude, I can estimate it, I can, write it in some other whatever. And in this way, I can go a step closer to having the distance. And the relation between inner product and distance is quite straightforward.
So what sort of speed up do I get? Do I converge faster? Or when you compare empirically classical k-means to q-means, what are some of the advantages you get?
Converging faster is not exactly the idea. To me, what you get is that each individual iteration of your centroid updating each iteration will be faster. Classically, to update to the one iteration, right, it's linear in the number of points. Let's say it's n. It's linear in the number of cluster or the number of centroids, which is k, and it's linear in the dimension. And here, quantumly, it's going to be logarithmic in the number of points n, because of this idea of being in superposition of all points while doing the distance estimation and so on. However, it will be a bit slower in the number of cluster k. Now it's k square quantumly. In terms of dimension, d is the same. But now, the main difference also is that quantumly, there will be a new source of randomness and noise, because again, when you deal with quantum state, quantum computing, there is a bunch of random process going on, because there is a probability of being in each state. So there is some kind of noise, let's say, we call it like epsilon or delta, and this noise is pretty impacting the result of the iteration. So each iteration will be quite faster and with respect to the number of points in the dataset, but on the other hand, it will be a bit more random, noisy.
One of the things that people will do in classical k-means is use a seed, so that despite the randomness, they can kind of have determinism and ending up in the same place. Are you able to offer any similar seeding option?
So I guess in k-means, the seed would be somehow the place where you put your initial centroids. And because in the q-means, we are actually using, again, these classical centroids as input, and we update and give classical centroid as output, it's the same. We could use the same seed. Actually, there is also another way to initialize k-means. Maybe you've talked about it, but it's the k-means plus algorithm, where you have this smart initialization. Well, in our paper, we propose a q-means plus in the same way. So there is a strong parallelism between k-means and q-means. So everything you would like to do with the k-means, you could be doing it with the q-means. It's just that you need a quantum computer, and the inside of the algorithm is quite different, but it follows the same step.
Well, inside the algorithm, as you'd mentioned, we go to a k squared now, but k is a constant, and a small one at that, usually, no big deal. And then we get a sublinear runtime for the other step. This has always felt a bit magical to me. Do you have any intuitive way of helping me understand how sublinear can possibly yield me a solution in a case like this?
Yeah, so this sublinear in n, the number of points, is due to this idea that I can prepare a quantum state. So I can also explain what is preparing a quantum state that is supposed to represent some vectors. But I can prepare a quantum state that is not just one vector, but a superposition of vectors. So instead of saying, okay, let's take 1 point and let's compute the distance to each of the centroids. So what we do with k-means, I say, okay, let's take all the points at the same time, and let's compute all the distance at the same time to one centroid, and then the other centroid, and so on. So when you take all the points and you compute just once the function saying, what is the distance between this and this? It goes way faster, right? So you have to call only once what is the distance function, but you will compute to all the points and one centroid. So this is the intuition behind. Of course, in practice, it's way more complicated, but yeah, that's the idea. And you cannot be better than log for some reason.
And could you explain QRAM and what the importance of QRAM is in the work?
QRAM stands for Quantum Random Access Memory. I don't know if it's a great term, but anyway, this is the one people use in the field. So QRAM is actually the ID. It's a circuit that you put at the beginning of your quantum circuit, right? And it's this circuit that's exactly what I was saying before, that allows you to prepare the quantum state. So let's say I have a vector x of dimension d, so just one vector. It has to be written in some kind of classical table, which actually should be some kind of binary tree, okay? And if you have this binary tree, you can construct a quantum circuit, and there are different proposals for such quantum circuits, but it's one quantum circuit. And you are ensured that at the end of this quantum circuit, the quantum state you have, because you started with the quantum state 0 everywhere, the quantum state you end up after this QRAM circuit is what I called the quantum vector X. What is it? It's actually a quantum state. It's a superposition of a fundamental state. So right, if you have a vector of dimension d, you only need log d qubit, and each of these qubits could be in state 0 and 1, okay? So because when I say log, it's the binary log, okay? And so how many combinations you can have on this log d qubit? Well, you can have d of them, because each of them can be in two states. So for instance, you would have 0, 0, 1, 0, 1, 0, 0, 0, and so on. The idea of the QRAM and this quantum state that is supposed to represent a vector is that the amplitude of each of these states like 0, 0, 1, 1, 1, 1, the amplitude would be one of the components of x, like first component of x, x1, x2, and so on. So kind of the probability of measuring 0, 0, 1, 1, 1, 1, 1 will be x5, for instance, and so on. And this is what we call the quantum vector.
Thanks to our sponsor, mParticle. At the end of the day, your customer has to be at the center of everything you do. This starts with the right customer data strategy, as well as the right foundation to solve the challenges that typically inhibit success, such as data quality, data governance, and connectivity. mParticle is your real-time customer data infrastructure that helps you accelerate your data strategy by cleansing, visualizing, and integrating your customers' data from anywhere to anywhere. Ultimately, better data leads to better decisions, better customer experiences, and better outcomes. See why the best brands choose mParticle. Visit mparticle.com to learn how teams at Postmates, NBC Universal, Spotify, and Airbnb all use mParticle's customer data infrastructure to accelerate their customer data strategies. That's mParticle. Better data, better decisions, better outcomes. Visit mparticle.com to learn more. Thanks to our sponsor, BB Edit from Bare Bones Software. If you're a Mac user and you have any need whatsoever for a text editor, which, let's face it, that's got to be all of us, you have got to check out BB Edit. BB Edit 14 provides Mac users the most powerful, professional-grade text editor around. It's known as capable and rock solid, and can process files that are large enough to bring other editors to their knees. This tool's been beloved for over 25 years, and I can understand why. If I'm just typing up some simple hello world, I guess any text editor will do. But when I really get into the weeds and need to do some data processing, maybe I've got a big messy file, I need to find all the non-ASCII characters and remove them, BB Edit's there for me. It has best-of-breed multi-file search and replace and great scripting support for text transformations. There's a whole menu of text transformations that you'll find handy. If you're a serious data scientist or software engineer, you're going to bump into situations where you need a powerful text editor. So download and try BB Edit today. You can get it at www.barebones.com. See how much your productivity can increase. barebones.com and download BB Edit. Well, in k-means, we have to have some sort of halting condition. An easy one is the number of iterations, right? You just count it. But a lot of people prefer when you have some sort of guarantee of you've converged to a closeness, epsilon close criteria to some precise answer or estimate of it. I understand how to do that in k-means when nothing is hidden from me in the quantum state. I can kind of look at all my data. Do you face any challenges in defining the halting criteria in the quantum algorithm?
Well, actually, there is no issue in using some halting criteria, and the reason is a bit like in the seed ID, because in each iteration, I start with classical vectors that I put as quantum vectors, do my business, and output a classical vector at the end, being the new centroids. Well, because I have the classical vectors at the end, I can use any of your favorite halting criteria. It could be threshold distance or whatever. So there is no difference on that matter.
So can you persist the quantum state from iteration to iteration, or is it kind of a start and stop the quantum process at each iteration?
Exactly, it's a start and stop. So it's a full quantum, I said before, but not in between iteration. So you're right. There are some reasons for that. It's a bit technical, but it's easier like that.
And then I guess one of the key insights is that you can calculate the distance in this quantum way. I'm curious if you think that trick can be applied in other places, like all pairs shortest path or Dijkstra's algorithm.
Absolutely. Actually, the first idea why we choose k-means as a first algorithm to quantize, let's say. This idea is that we figured out that calculating the distance was possible. So we choose like the most appropriate and simple algorithm for that is distance-based. And k-means felt quite simple. But then we generalized this idea to new stuff. For instance, Gaussian mixture models, and later on spectral clustering, which was quite more complex, let's say, but the idea stays the same. And let's say that in general, being able to compute the distance and being able to access the metric of a data space is extremely useful in so many applications.
I'm glad you brought up Gaussian mixture model. I wanted to ask about that. At a surface level viewing, it sounds very similar to Q-means, right? Gaussian mixture model is K-means but probabilistic, essentially. Quantum is classical but probabilistic, essentially. Could you contrast the differences here?
So to us, and again, I didn't precisely work on Gaussian mixture model, it's a colleague of mine. To me, the idea was instead of finding just one centroid, right? You want to find one centroid plus some covariance matrix that tells you, okay, you're not just looking at a sphere around the centroid, but you're looking at a shaped blob around the centroid. So that's the way I understood it. So it's still it's the same idea. You want to update the centroid, but you also want to update this covariance matrix. So on the probabilistic side, to me, it's kind of the same again. You just need to remember that using quantum will add more error, more randomness. And there is nothing you can do about it except pushing the limit of your quantum computer in terms of depth, in terms of time of computation to reduce it.
Well, as we look at the asymptotes of any computational theory problem, we know what happens as n grows larger. So I can see from the formula that I'll refer listeners to read in the paper because it's a little long to read out loud. Your algorithm will, in the horizon, outperform classical k-means. But for small data sets, these constants and things kind of matter. Practically speaking, at what size does your approach start to yield benefits on today's engineering prowess?
Yes, so you're right. The actual running time, if you look at it, it's a bit awful, right? There are plenty of parameters that.
To read out loud, it's a good result, though.
Yeah. Even to look at. So and by the way, that was one of the interesting aspects of this work is to discover that some parameter appears in the running time that are counterintuitive. For instance, in classical computing, the value of the component of your vector, they don't interfere with the running time. Like if you are processing numbers that are where the value are like more ones or more 10,000s, it shouldn't change, right? Actually, with quantum computing, we realize that it does. It's pretty weird. But apart from that, we were able to simplify this running time, which is super long, to something which is a bit more compact. For that, we had to do some assumptions. And these assumptions are the well clusterability, as we called it, the fact that you indeed have clusters that are little spheres that are far from each other. If you have this assumption, then the running time becomes very shorter and nicer to read. So when does it become practical? Yeah, I think it's hard to tell because in addition to the running time, because you can see some overhead and so on, I'm sure that in practice there will be much more problem using quantum computers, right? So this is a theoretical paper showing asymptotic stuff, but in practice we must be aware that things will be way more messier, okay? So I cannot have a straight answer. And it would be a bit of a lying telling you, all right, if you have a data set with 1 million points, then the quantum computer is amazing. It's not that obvious to me. First, we need a fault-tolerant and big quantum computer in any case, at least to implement this QRAM part. We need something that doesn't have too much qubit errors and so on. Again, that's the job of the experimentalists and the engineers. But so yeah, I don't have the clear answer, and I wish I have it.
I think we all do, though. You'd mentioned the term shallow earlier. Could you describe what you mean by a shallow quantum problem?
You can imagine the depth of your quantum circuit as the number of gates, right? So if you want to draw this quantum circuit on a paper or something, it's like you could measure it in terms of centimeters, right? Or inches. Shallow would just mean that you have not that many gates. And in particular, you want it, imagine the number of qubits is d. You want something that doesn't scale like a square of d or exponential of d or whatever. And actually, if it's sublinear in d, it's even better. And then you can say, oh, right, it's shallow. But actually, right now, with the quantum computers that are available, you can play with like 8 qubits, 16 qubits, or 20 qubits. And I know that some of them are more like 80 qubits or 100, but I haven't tried them. So something that is shallow is just something that doesn't fail in a sense. Each time you add some depth, the error will accumulate more. So of course, the shorter, the better.
When you describe it as shallow, that makes me think of like algebraic circuits, which are nice for analyzing and being able to do like formal proofs from a theoretical computer science point of view. But I think that's not necessarily the shallow you're concerned with. Yours is more like in practice, the engineering side of being shallow. Is that right?
Yes, you're right. Both approaches are good in the sense that you can have theoretical ideas about why shallow could be great or what are the limitations of using shallow circuit and so on. But in my experience, it's just that really for now with the quantum computers that are available, the shorter the better in a sense. Like you can clearly see that the errors accumulate. So yeah, both perspectives are complementary.
But it's errors that we're fighting, I guess. Interesting. Are you aware of any of the experimental groups that are building these machines that are looking for algorithms? Have they taken an interest in your work as one of the possible candidate things that they'll run for doing their benchmarking?
Yeah, so I closely follow all the improvements in many types of quantum computers, in particular the new ones, and because you have of course the big the big corporation and universities that are here for a long time, but I also like to look at the new experiments and the things that are a bit more original, let's say. But anyway, in the Q-means algorithm, this one, I'm not sure it's like a current benchmark or a current thing that people are interested in, because again, it is designed for long-term and, perfect quantum computers, which we don't have right now. That being said, in the meantime, because this was one of my first contribution to the field, in the meantime, we proposed in my group new algorithm, and some of them are quite shallow. So we were able to implement them in actual quantum computers, because here the Q-means was impossible. So we had to simulate it. And we could talk about how do you simulate a long-term quantum algorithm like Q-means to compare it with K-means. And let's say that just this later work, which are more near-term, get more interested, of course.
Yeah, does that simulation mean you just have to kind of exhaustively check all the quantum states, or can it be done in some faux efficient way?
Yeah, so usually when you talk about simulating a quantum circuit, that's what you do. You implement classically each quantum state. It's just that then, because you can always be in superposition of two states, everything becomes exponentially larger. So if you have, for instance, d qubits and you have one quantum gate acting on this d qubit, well, to represent the input vector, you need an exponential d size of vector. And then matrix that is representing the gate is also exponential d. So it's too big for a classical computer. So you could do classical simulation of quantum circuits up to, let's say, 30, or maybe I heard 40 qubits in specific cases. In the case of Q-means, this is not what we have done. The good thing about Q-means is that we know exactly what is going on at each step. So exactly in theory, right? We cannot understand what will be going on due to the noise of the qubit being not perfect and all. But we know what is going on when I take the centroids, I take the vectors, I compute the distance. There is some randomness, there is some error, and we know exactly what it is. So the idea was to simulate the Q-means easily in the following way. We take K-means algorithm written in Python, usual way, and then we add some, let's say, quantum spice, right? At each step, adding this randomness, adding some noise. For instance, when you compute the distance between two vectors, you add a bit of noise. When you choose the minimum distance among different centroids, well, you add some randomness. So maybe you would make an error. This kind of stuff. So we can play with the error magnitude or the randomness magnitude. And in this way, we can simulate what this algorithm will do on a perfect long-term quantum computer.
Let's delve into some of those empirical results then. What do you find in terms of performance comparing the two?
We used the MNIST dataset, and we did unsupervised clustering on the MNIST images after some simple PCA, I guess. And somehow you can look at each iteration how the accuracy is improving. And then we launched the same experiment using K-means. And we played with this error parameter somehow. So what we observe is that it's kind of learning in the same way. It's converging anyway. If the error is small, of course, it becomes exactly as the K-means. But if the error is too big, it still converges, but you can see that it has more trouble to do it, and it reaches far lower accuracy. The thing is that this noise parameter, as I said before, it's appearing in the running time, and it's like the inverse of this error in the running time. So in theory, you would like to have a big error so that the runtime is faster, but then you have to, it's kind of a no free lunch, right? It's a trade-off with the accuracy compared to the classical K-means.
Long term, do you see that as a hyperparameter a machine learning practitioner might refine for their own problem?
Yeah, absolutely. I think this error parameter is interesting. And also something else that it's still kind of an open question is that in any type of quantum algorithm, whether it's a long-term or a short-term ID, there will be this noise, this randomness. First, because of the probabilistic nature of quantum, but also because of the noisy nature of these qubits, this quantum stuff, this engineering. There will be some noise. So because of that, there will be no perfect calculation, computation. Now, the question is like, in which case this noise could be useful? We know that in some of machine learning area, people, they tend to artificially add some noise, thinking about escaping a local minima or in neural networks and so on. So maybe this natural hyperparameter, which is quantum noise, could be interesting. But again, I really don't know.
Well, definitely interesting stuff to look into in the future, I guess. I know you've also looked into a number of other quantum algorithms. One that jumps out from looking at your CV is quantum spectral clustering, just because of its relationship to k-means. Could you talk a little bit about that paper and what the key quantum insight is there?
Yeah, so I think that after we did the q-means, the natural next step, okay, there was the Gaussian mixture model, of course. The natural next step was also to look at a classical algorithm that is actually hard to do, because k-means is linear in the number of points, so in practice you can do k-means. But it was a good training for us. Now, spectral clustering, first I find it more elegant, let's say, in terms of mathematical formulation, but it's also more performance in terms of if you want to cluster more complex, let's say, nested structure or non-convex data, spectral clustering is a better solution. And you can see that the accuracy is way higher than k-means. The drawback is that it is now cubic in the number of points, so it's n to the cube. So here you have a classic algorithm that people cannot actually use in practice if you have too many points. And for us, it was a good opportunity to tackle a more complex mathematical algorithm. Because for spectral clustering, not only you have to compute, the distance between the points, you also have to compute some kind of graph to derive from this graph a Laplacian matrix, and then to perform some projection, etc., etc. So it was way more complicated for us to come up with a quantum algorithm in the same fashion. So again, if you're not familiar with spectral clustering, you want to project your point in some space, and this projection is done through this Laplacian matrix of the graph. And in this space, you would apply k-means, and that we know how to do. But the new part was how to project this point in the space, how to have this quantum Laplacian matrix, and so on. So in the end, we found something. It was very fun, actually, to do and to understand these graph properties, how to project on the lowest eigenvalues of some graph matrix and so on. So very interesting. But we were able only to provide a quantum algorithm that is linear in the number of points. So we go from cubic to linear. And we did some simulation somehow, and we did observe this cubic to linear thing, knowing that quantumly the linear is the worst case, but we think that the worst case will be reached in any case. So yeah, spectral clustering was fun, just that we don't have this exponential speedup we had in the k-means. The main reason being that if you want to access this idea of eigenvalues and projection, then it's much more complex. Quantum can help, but not as good.
Well, these and other areas of your work highlight a number of places in which quantum definitely can help. I think in large part, theory is ahead of engineering in 2022 as we speak here. Do you have any prediction for a point, even if, will happen in your working career, when you think some of this theoretical work will be practically implemented at large and, important scale problems?
First, your first remark about is theory ahead of engineering? Yes and no, in the sense that, of course, we can start to think about what we will be doing with a perfect universal quantum computer. So we are ahead in the sense, but I'm not sure we have found the perfect application, the perfect algorithm yet. So yeah, okay, I agree. In the long-term algorithm, they know what they want to do, of course. But in the near-term algorithm, we don't know what we want to do because it's a totally different approach. So in the near term, I would say that engineers and theoreticians, we are on the same step. Now about the prediction and say when we will have this machine, it's super hard to answer. And I think that listening to some of the great speakers and researchers, because this question is asked every time, I will tend to follow their lead and say I cannot answer because I will be wrong. So I don't know, I just hope that it will be sooner than later. But also when I hear these speakers that have a big career, right, behind them, they say 20 years ago, if they have been told that we would have a 50 qubit or 100 qubit quantum computer in 2020, they wouldn't believe that it would have been true, So we can be optimistic, But again, we are trying to put nature in a box in the way she doesn't want. So let's be optimistic, but let's be realistic also. I hope that in my lifetime, I will be able to implement at least some part of the work that I am doing. This is the best I can hope for.
I think that's a great perspective on it. Jonas, where can people follow your work online?
Yeah, I mean, unfortunately, I don't have Twitter, so I'm not on Twitter, but I do publish papers on the archive. I do also have some blog posts on Medium from time to time, but that's all. I recently put the whole PhD thesis on the archive, so I guess you just have to type my name, right? So Jonas Landman, but that's all I can give you, I guess.
Oh, that's more than enough. I found you on the archive, and I'm glad I did, so we'll have links to those things in the show notes. Well, Jonas, thank you so much for coming on Data Skeptic and sharing your work.
Thank you.
That concludes another installment of Data Skeptic K-Means. Thanks to our sponsors today, mParticle and BB Edit by Barebones Software. Myself, Claudia Armbruster, as Associate Producer, Vanessa Bly, Guest Coordinator, show notes by David Abembe, and our host, Kyle Polich.